Imagine two ice skaters standing still on nearly frictionless ice. They push away from each other, and suddenly both skaters move in opposite directions. Before the push, nothing was moving. After the push, both are moving. So, where did the momentum come from? The answer is that the total momentum of the two skater system stayed the same. One skater gained momentum in one direction while the other gained momentum in the opposite direction. Those momenta balance each other. In this video, we will learn the principle of conservation of linear momentum. We will first define internal and external forces and then see how momentum can be conserved during a collision or push-off, and finally solve an ice skater recoil example. To understand when momentum is conserved, we first need to distinguish internal forces from external forces. Internal forces are forces that objects inside the system exerts on each other. External forces are forces exerted on the system by something outside the system. This distinction is essential because internal forces can change the momentum of individual objects, but they cannot change the total momentum of the whole system. For example, if the two skaters are our system, the push they exert on each other is an internal force. The woman pushes the man, and the man pushes the woman. These forces are equal in magnitude and opposite in direction, so their effects balance when we look at the total system momentum. External forces are different. If the flow, ground, air resistance, or another object outside the system exerts a net force, then the total momentum of the system can change. So, the first step in any momentum conservation problem is to choose the system and ask, are the important forces internal or external? Now, let us see how this idea applies to a collision between two cars. This slide shows two cars moving in the same direction. The first car bumps into the second car. During the collision, each car's momentum changes. The first car slows down and the second car speeds up. So, if we look at each car separately, momentum is not constant for either one. But if we treat both cars together as one system, the total momentum can remain constant. Before the collision, the total momentum is the momentum of the first car plus the momentum of the second car. After the collision, the total momentum is again the momentum of the first car plus the momentum of the second car, using their new velocities. If friction and other external horizontal forces are negligible, then the total momentum before the collision equals the total momentum after the collision. This does not mean the cars keep the same speeds, it means the combined momentum of the system stays the same. Momentum can be transferred from one object to another inside the system. Next, we state this idea as the formal principle of conservation of linear momentum. The principle of conservation of linear momentum says the total linear momentum of an isolated system is constant. An isolated system means the net external force on the system is zero, or close enough to zero, during the time interval we are studying. This principle comes directly from the impulse momentum theorem. Net external force times the time interval equals the change in total momentum. If the net external force is zero, then the change in total momentum is zero. If the change in total momentum is zero, that means the final total momentum equals the initial total momentum. This is the main equation we will use. But it only applies when the system is isolated. or when external forces are negligible in the direction we are analyzing. Now let us apply this principle to two ice skaters pushing away from each other. Two skaters start from rest on ice where friction is negligible. They push off against each other. One skater is a 54-kilogram woman and the other is an 88-kilogram man. After they push away, the woman moves with a speed of 2.5 meters per second in the positive direction. We are asked to find the recoil velocity of the man. Because the skaters start from rest, the initial total momentum is zero. Since friction is negligible, there is no significant external horizontal force on the two skater system. Therefore, the final total momentum must also be zero. This means the woman's momentum in the positive direction must be balanced by the man's momentum in the negative direction. Before solving, let us predict the result. The man has a larger mass than the woman, so he should recoil with a smaller speed. Also, because the woman moves in the positive direction, the man's velocity should be in the negative direction. Since the system is isolated in the horizontal direction, total momentum is constant. So the total momentum after the push equals total momentum before the push. The skater starts from rest. So the initial total momentum is zero. So we can write final total momentum is zero, and that means m1 v final 1 plus m2 v final 2 equals 0. Now if we want to find v final 2, we can rearrange this equation. So we can send m1 v final 1 to the right hand side of the equation. We get m2 v f2 equals negative m1 v f1, and then we can divide both sides by m2. We find vf2 equals negative m1 vf1 divided by m2. And now we can substitute the values. So vf2 equals the mass of the woman, 54 kilograms, times the velocity of the woman, which is positive 2.5 meters per second, and divided by the mass of the man, 88 kilograms. And we get negative 1.5 meters per second. The negative sign is important. It tells us the man moves in the opposite direction from the woman. The magnitude 1.5 meters per second is smaller than the woman's 2.5 meters per second because the man has the larger mass. This example shows the central idea of momentum conservation. Internal forces can make objects move apart, collide, or change velocities, but if the net external force is zero, the total momentum of the system remains constant.